Hello everyone. We want to do a little bit of extra practice on limits, so today I want to go through at least one example of every type that we will look at this semester. So the first problem we're going to do is a rational function that when I try to evaluate numerator and denominator at 4, we see both numerator and denominator tend towards 0. That means this is an indeterminate form 0 over 0. 0 over 0 is not the answer, it's not a value. We are approaching this form, which tells us our strategy is to factor and cancel because those are both polynomials. Now, they're both third-degree polynomials, so factoring might be a little bit of a challenge. So what I would suggest for the numerator is to use longer synthetic division. So let's use synthetic division on that one. With a root of 4, that means I'd have 4. I write the coefficients in descending order. Since there's no x term, that's a 0. Remember to bring down the first term and then multiply and add. Multiply and add. Multiply and add. And that 0 tells me I have a remainder of 0. So what I have left, constant term, the x squared. So I know then that my numerator factors as x minus 4, 3x squared minus 2x minus 8. Now my denominator is the difference of cubes. So I can use longer synthetic division or just remember the formula for difference of cubes. So that's x cubed minus 4 cubed. So it would be x minus 4, x squared plus 4x plus 4 squared. Now at this point, I have factored successfully, and my problem child, the x minus 4, I can now cancel and remove it from the problem, thus making it a removable discontinuity. So now if I evaluate the numerator at 4, I'd get 48 minus 8, which is 32. The denominator, 16 plus 16 plus 16, which is 48, or simply 2/3. Now, like the previous example, as x tends towards 8, my numerator clearly is approaching 0. My denominator is approaching the square root of 16 minus 4, which is also 0. So, like the last problem, this has the indeterminate form 0 over 0, but unlike the last problem, it's not as simple factor and cancel because the denominator is not a polynomial. I need to get the denominator to have an x minus 8 in it. The simplest way to do that is to rid myself of the root in the denominator, and the best way to do that, of course, is to multiply by its conjugate. So we will multiply the top and bottom by the conjugate of the denominator, root x plus 8 plus 4, root x plus 8 plus 4. Now I do want to distribute the denominator, but I will leave the numerator in a factored form because, again, it's the x minus 8 term that I'm trying to get rid of. So on top I'll have x minus 8 times the quantity, the root plus 4. Now on the bottom I have something of the form a minus b times a plus b, and when you multiply conjugates, as you remember, you get the difference of squares. So it'll be the square of the square root, which would simply be x plus 8, minus the square of 4, which is 16. So x plus 8 minus 16 is simply x minus 8. And I have accomplished my goal of creating a situation where, again, I can factor and cancel the thing that's causing problems, the thing that's going to 0. So after I do that, I am left simply with root x plus 8 plus 4. My denominator cancels. Now as x approaches 8, this term is approaching root 16 plus 4, which is simply 4 plus 4, or 8. Now, as I let x approach pi over 2, my numerator will approach the tangent of 0, which is 0. My denominator will also approach 0. So once again, I have the indeterminate form 0 over 0, but now I have it in a trig case. So I either need to get the sine theta over theta form or the 1 minus cosine theta over theta form. But as I look through this problem, what do I actually identify as theta? Well, it turns out the argument must come from that guy right there. So if I think of my theta as simply being 2x minus pi, then if I multiply numerator and denominator by 2, I will have a 2x minus pi in the denominator, and I will then have the form tan theta over theta. Now the problem is, what about this statement here? Well, as we've seen before, as x approaches pi over 2, then x minus pi over 2 must approach 0. And if I take 2 times x minus pi over 2, that must approach 2 times 0. So 2x minus pi approaches 0 also. So at this point, I can rewrite the problem as 2x minus pi approaches 0. I have 2x minus pi in the denominator. I have the tangent of 2x minus pi in the numerator. And this 2 here, we can simply pull out in front. So now I have the form, limit as theta goes to 0, tan theta over theta. That's the form I have, and we did a problem like this recently in class. And all I need to do is change the tangent into sine over cosine, and this will become 2 times the limit as 2x minus pi approaches 0 of the sine of 2x minus pi over 2x minus pi. I'll erase this. Times 1 over the cosine of 2x minus pi. So I have sine over cosine, but if I write it as a product there, then it's easier to separate these limits. So finally, the limit as 2x minus pi approaches 0 of the sine of 2x minus pi over 2x minus pi times the limit as 2x minus pi approaches 0 of 1 over the cosine of 2x minus pi. Now I have exactly the form I need. We know that's an identity. That is equal to 1. This over here, as 2x minus pi approaches 0, the cosine of 0 is 1, so this quantity is 1. This quantity is 1 times 2. So my final answer is 2. Now you notice we're going to take a limit as x goes to infinity, so both numerator and denominator are growing without bound and approaching the indeterminate form infinity over infinity, which is the other one that we look at in this course. Now this isn't a factor and cancel problem. Even if this could factor and cancel, that wouldn't help me because both of these are getting infinitely large. So instead, we will do a little bit of algebra. Now I have one of two choices here. Either I can factor out an x cubed from the top and bottom, or I can simply multiply top and bottom by 1 over x cubed. Turns out that's actually a little bit more efficient. So if I said I'm going to multiply by 1 over x cubed over 1 over x cubed, well, x is growing. X isn't 0. That's the only time I can't do that is if x can be 0. So when I do that move, I get the limit as x goes to infinity of 5 minus 3 over x on top, 2 plus 6 over x squared plus 1 over x cubed. Now, as we know, the limit of a quotient is the quotient of the limits, and the limit of a sum is the sum of the limits. So quite literally, I can work the limit into each term. So without rewriting it, this essentially is the limit of 5 minus the limit of this over the limit of 2 plus the limit of this plus the limit of this. Now, as x grows without bound, these three quantities all approach 0. There is no value of x that they will ever equal 0, but as x grows without bound, these become infinitesimally small. Therefore, my limit, what's left over, is simply 5 over 2. Now, you could also have made the argument, because this is a rational function, a quotient of polynomials, I could simply have looked at the degrees of the highest terms. And because the degree of the numerator, I'll abbreviate, equals the degree of the denominator, we know we could have just taken the ratio of the lead coefficients to get the same result. But this is a more formal mathematical approach. Now, of all the problems we look at, this one tends to be the most troublesome because this is not an indeterminate form. As x approaches 6 from the right of 6, meaning from numbers bigger than 6, my numerator is approaching 4 minus 6 squared, which is negative 32, but my denominator is approaching 0. Now, if I just simply said negative 32 over 0, that is undefined. And undefined isn't even an option for a limit question. It's an impossible answer. A limit cannot be undefined because you cannot divide by 0. So I have to go back and look at this statement here. As x approaches 6 from the right of 6, that means x is always bigger than 6. That means 6 minus x will always be negative. So I am approaching 0 from the left of 0, and that's huge. Now, when your denominator is approaching 0 and your numerator is not, we call this an asymptotic discontinuity, meaning basically I have a vertical asymptote in the graph. But the question is my graph going this way or is my graph going this way? We know that the graph is getting infinitely large, but is it positive infinity or is it negative infinity? No amount of calculator work will help us here. I simply look at the behavior. Since my denominator is approaching 0, this quotient is growing without bound. My numerator is negative and my denominator is always negative because I'm approaching 0 from the left of 0 through negative numbers. That means that this quotient is always positive. It's growing without bound, it's always positive. That means the answer is positive infinity. There is no algebra to perform. Now do notice, had I approached 6 from the other side, from the left of 6, the numerator would still be this, but the denominator would have been approaching 0 from the other side, which would have changed the sign of my final result. So in this type of discontinuity, the most important part of the problem is identifying from which direction we are approaching 0. The algebra is trivial, but conceptually this one's a little bit gnarlier. Now here's a bit of a bonus question. Like before, I'm approaching infinity, but this is not a rational function. Numerator and denominator are growing without bound, but this isn't really a factor and cancel. This isn't a degree of the polynomial type of problem. So the question is, how do I make this work? Well, let's look at the 4x to the 4th minus 3x term to start with. I want to factor out x to the 4th. So if I factor out x to the 4th, that would leave me with 4 minus 3 over x cubed. So I know this is a true statement. Secondly, if I said, well, then what's the square root of this? Well, then that would be the square root of this, and the square root of x to the 4th would simply be x squared. So here's the key to doing this. My first step of the problem, I'm going to factor the numerator as x squared times 4 minus 3 over x cubed. Now, if I do the exact same thing to the denominator, if I take x squared plus 2 and I factor out the x squared, that would leave me with 1 plus 2 over x squared. So my denominator is x squared times 1 plus 2 over x squared. And now notice I can cancel the x squareds. So when I do that, what I'm left with, I have the root on top. I have 1 plus 2 over x squared on the bottom. But now as x grows without bound, this is not growing without bound on top and bottom. In fact, as x grows without bound, this term here is approaching 0. This term here is approaching 0. So my limit would simply be the square root of 4 over 1 or 2. Now this one was a mouthful. This was a difficult problem. But we attacked this in the same way as we attacked the other infinity over infinity forms. And that's essentially to factor out the highest degree term, cancel it if we can. Now you've got a pretty good showing here of every type of limit you could run across in a Calc 1 class. So be mindful and try to be able to do all of these on your own at some point.